Hello, everyone. It's me, Carolyn, and I have broken this module or this unit. I guess there's two modules that kind of combine parts of modules 14 and 15 into one unit. We are not going to be covering all of 14 or all of 15. I just kind of, because this is an introductory course, so we are just going to be touching some of these ideas. So first of all, I want to kind of remind us what we do have these symbols that show up in our formulas, and it's kind of nice to remember what they stand for, and what they are. So first of all, this is X bar, and it is our sample mean. So that means it is a statistic because a statistic is something that is calculated on the sample. This is mu, which is a Greek letter, lowercase Greek letter. It stands for the population mean. So it is a parameter. And those ideas will become important in this unit and the next. S is just S, but it does stand for the sample standard deviation, which is a measure of how spread out our data is. The smaller the number, the more tightly compact our data is, and it will affect how some of our distribution curves look. This is sigma, the lowercase Greek letter sigma. Capital sigma was this guy. He told us to add things together. This happens to be our population, sorry, standard deviation. Okay. Up until now, when we were looking at probabilities, we were just looking at what is the probability that a single person or a single item in our distribution was between two values, less than a value, at a value in the case of a discrete. But what happens if we look at a group of people and we want to know something about their average? So basically, instead of looking at a single person, being able to calculate the entire population average, we always take these samples. So let's say that I took a sample of 8 men and I found that the average was 68.8 inches. Now, that might be pretty close to the real population average, but I have really no way of knowing. So how could I get a better average? How could I get a better estimate? Well, what we could do is we could look at a different 8 men. So I could then maybe do a different 8 men, and what if I then did that, got the 67.9? What if I averaged those two values together? So then I'd be looking at 16 men. What if I took 1,000 different samples of size 8? And we looked at all those different samples and we started maybe graphing what those numbers looked like. So we'd have 1,000 different sample averages. Well, it turns out that if you do that, there's some really nice outcomes. So first of all, if we do that and the original data was the mean, if you took the average of all of our averages, so the average of all of our averages, that's what this is, we would still get the average of the entire population. The reason for that is if we take all different possibilities, we will have every single person in at least one or two or lots of those samples. So we would have been adding them in and averaging them in. The standard deviation of the sampling distribution does get smaller. So this is the spread or the standard deviation of all of our averages. That's the symbol we're going to kind of use. And it turns out, and we're not going to go through why, if you want to, you could probably go on further in your statistical courses into some of the more theory-based courses and learn why this is actually the case. But it turns out to be the actual standard deviation divided by the square root of n, depending on how big your sample set size is. This is sometimes called the standard error. So if you hear the word standard error of the mean, think of it as the standard deviation of the averages. So how spread out were the averages of our set? The reason it is smaller, because we're dividing by a certain value, is because we're kind of averaging out the extremes. Because no longer is that one extreme being by himself pulling things down. He's going to be averaged with some other people before the pull is. So his pull becomes a little less drastic. That's how I like to think of it. We're averaging out the extremes. Rule number 3 tells us what the shape of this thing is going to look like. It turns out that if our original population was normal, our sampling standard deviation will also be normal. Notice though that rules 1 and 2 will happen no matter what n is. Rule 3 only happens if it is normally to begin with. So what does this all mean? How can we put it all together? So what this kind of lets us know is, suppose we have IQ scores, and these are just some examples I made up, and that they can be modeled with a mean of 100, standard deviation of 15. What can we say about the sampling distribution of the sample means? So if we're looking at all of our little X bars, what will it look like, and what can we say about it? Well, since the original stuff was normal, I know that this X bar will be distributed normally. It will be normal. So it's going to follow that normal curve. It will have a mean equal to the same as the mean before. But its standard deviation, or its standard error, is going to be a little bit smaller. It's going to be that 15 divided by our sample size, square root of our sample size. Because again, we are averaging out the extremes kind of thing. So that is all it's telling us. We will then eventually be asking questions about, if I take a sample, what's the probability it's going to be in this range or bigger or smaller than this value? But being normal, that tells me I'll be able to use my normal curve. Here's another example. And we might use these examples later on as well. Golf balls are manufactured. Random samples are tested for compression strength and other characteristics. Periodically, samples of size 10 are taken and tested for distance travel after being hit by a mechanical golf club. If the balls are manufactured correctly, the distance is known to follow a normal, with a mean distance of 185 yards, standard deviation of 20. So we are going to kind of describe what we have going on about these samples that we take. So we're supposed to define the sampling distribution of the sample mean. So thinking sample mean, that's X bar. So how is X bar distributed? So X bar, since our original, they are manufactured correctly, will be, so X bar, if this is normal, X bar will also be normal. The mean of our X bars will be the same as the mean of our original data, so 185. But our standard error, or that standard deviation of the means, is a little bit smaller than the original data. So we get that slightly smaller piece. And if you want to see that it is in fact smaller, drag out your calculator and do the math. And I get, this is about 6.32455, and there's a few more digits. So, okay. But a lot of times we don't, maybe if we're doing this, we don't even know the original, how the original stuff is distributed. So here's kind of a picture. So here's our population curve right here. Okay, so notice that if his population is originally normal, and now we're looking at what X bar looks like, knowing that the standard deviation is going to get slightly smaller, so it's going to be slightly grouped together. And if you remember our discussions on what the curves look like, standard deviation getting smaller makes it steeper. Notice these are all centered around the same value because the mean of the averages is still the mean of the population. Here's what happens if n is 4. Here's what happens when n is 16. We did this also if we look at just other populations. So let's say that this is a population. Notice this one is skewed to the right. We have that tail going off to the right. If we have just a sample size of 4, and I look at what those X bars will look like, and these curves can be created using simulations. So we can type in a population distribution and then just have it run a bunch of different X bars and start to look at what those values look like. If we get n being 16, notice that curve. It looks pretty close to normal already. So it turns out we have another rule, and this is a pretty powerful rule. Again, we are not going to prove it, but it is out there. So it tells us that when n is large, that the sampling distribution is well approximated by a normal distribution, even if the population wasn't normal to begin with. So no matter what the original population is, how it's distributed, whatever its original curve looks like, uniform, bimodal on two ends, who knows? Eventually, the samples will tend to look normal. The question is, how large does n have to be for us to have this normality? The rule of thumb that happens, notice in this picture, it took only till about 16. The rule of thumb, though, is if we can get bigger than 30, we will be pretty normal. So let's look at a couple more examples. So let's say we have third grade students in a large school district took a standardized reading exam. The distribution scores out of 50 had a mean of 39 and a standard deviation of 10. Most of the students performed well on the exam, but a few did poorly. So if you think about what it would look like, we'd have a bunch of people up on the top and we'd have a few people down here. So it would look skewed to the left. If we take samples of size 35, what will the sampling distribution of X bar look like? So since our sample size is 35, which is bigger than that magic cutoff line of 30, it would tend to be normal. X bar will be roughly normal. So we will be allowed to use that normal curve. And further, we always have rules 1 and 2 happening, not necessarily the normality, but rules 1 and 2 will always happen. The mean of our averages will be the mean of the original data, which would be 39 in this case, and our standard error is going to be that 10 divided by the square root of our n. This is going to be an important thing to remember when we are looking at our X bars. So let's continue doing some more stuff with this. So using this, from our previous chapter, we did look at a z-score. Okay, we can look at z-scores for our sampling distribution of X bar as well, if we have normality. So this works if X bar is normally distributed. If it's not normally distributed, then we have to look at some other things. Okay, we can calculate a z, which is X bar, whatever our sample mean was, minus the mean of our population. And this should actually have a little X bar across it if you want. But again, remembering mu of X bar is equal to mu. And notice this down here, we have that sigma over the square root of n, which is sigma. Is this different? Actually, it's not. So if you remember our z-score, it's our data value minus the mean over the standard deviation. If we're talking about X bar, we have X bar minus its mean, which is still mu, but its standard deviation is actually that sigma over the square root of n. So it is exactly the same idea, just we have to make sure to put in the correct pieces for the situation we have. So let's do some problems of how we're going to apply this. Again, we will be using SALT because SALT helps us, but I like to draw our pictures and write the probability statements as well that go along with them. So we can kind of let SALT help us. So we have these third grade students. This is the same example that we just saw earlier. Distribution, scores out of 50 had a mean of 39, standard deviation of 10. Most students performed well, but a few did poorly, so the distribution is skewed left. We took a sample of 35 student exams, and we want to know what is the probability that the average of this sample was less than 37. So we want to know what is the probability that X bar is less than 37. Now, if we were using tables, we would have to make sure to standardize this. But again, we first need to make sure if we can use a normal curve. And we can, since our n is 35, sample size is 35, that's bigger than that nice cutoff of 30, we don't need normality of the original data. And good thing because we didn't have it. But now this tells us that X bar is normally distributed. I'm going to abbreviate distributed, which means it follows this beautiful normal curve. And the mean of X bar, the center of our curve, is going to be the same as the center of the mean of the original data. Although the mean of the original data was skewed left. Once we start looking at X bars, it's going to turn out to be normal. And I want to know what is the probability that my X bar is less than 37. So 37 being down here, we want to know less than. The thing I also have to remember is the mean of my X bar is my 39. But I also need to know that the standard error or the standard deviation of what I'm looking at, X bar, is that sigma over the square root of n. And in this case, it would be 10 over the square root of 35. I will need this decimal when I go to SALT. Unfortunately, SALT does not allow me to put in the square root. So let me do 10 divided by the square root of 35. I need to get that value in decimal form. I get 1.69, and then there's a 0, so I'm just going to go with 1.69. You can put in more digits. Maybe I will put in some more digits just to make sure. I don't know how many SALT will allow me to use, but those are the ones my calculator gives me. So now I'm going to go to SALT. And when I go to SALT, so let me share that screen. You have to excuse my cough today. I do have a slight tickle in my throat. We are going to be still using our distribution calculators. And we're still going to be using our normal curves. Okay, right now the default when you go in there fresh is your standard normal, which has a mean of 0, standard deviation of 10, or 1, sorry. Our mean for the situation we're looking at is 39, because that was the mean of our population, the mean of those test scores. We are looking for X bar, so we need the standard deviation for X bar, that standard error, which is 10 divided by that square root of 35. So we do have to put in that 1.69, and I'll put in 0.3, 0.8, 5, 0.9. I don't think when I did this in my notes, for the answers in my notes, I used that many decimals, but that is okay. We are using a left tail, so hopefully now by this time you should be getting more comfortable with using the buttons in between here. The left tail, the right tail, both tails are between. We are looking for what is X bar. Notice our X is now X bar, less than 37. And our probability turns out to be 0.11836. If I had just typed in the 0.069, we'll see how much that affects it. Notice it did not affect it a whole lot. So the rounding of our, whoops, got to make sure to make that 37. There. Turned out to be 11832. I'll write that down as well. 1.69. Yeah, so I would recommend putting in a few extra digits if you have them, because why not? And you'd have an actual more accurate answer. So you can get that. I'm going to go back to our camera, and I wrote those in for us. While it's refreshing, I'll grab a drink of orange juice here. There we go. So we have X bar, probability that X bar is less than 37 is 0.11836. Notice I wrote on here, if we did round it a little bit. So not a lot of difference in our probability for that rounding. Let's do another example. Okay, let's suppose Hy-Vee records show the amount of that each person spends per visit. The mean sales is $20.50, standard deviation of 3.05. First thing I ask is, what shape would this take on? And this is really a guess, because you're kind of trying to figure out, okay, what would it look like? Do a lot of people does it take a normal curve on, where we have a lot of people in the middle, a few on the bottom, and a few on the top, which could be the case. I don't know if that's the case. I think when people go to the grocery store, I don't think we get a lot of the lower end of people buying just a little bit, like taking and running in for one or two things. I feel most, especially at Hy-Vee, I think if people go to Hy-Vee for groceries, they're going to be doing their majority of grocery spending. But you may have a few people that spend lots, the people with the huge families and things like that. So I feel this one might be a little bit skewed to the right or normal. It's really hard to tell without actually going and collecting data. So that's kind of what we would have to do in situations, is try to figure out what does the shape take on without actually doing any data. And a lot of times we don't know. So, but let's suppose they then went further. So this may be normal. I don't know, maybe skewed to the right. I don't think it's going to be skewed to the left, because I think that based on my shopping habits and what I've seen at shopping stores, I'm thinking it's going to be one of those two, where we see a lot of people, either a few on the ends and mostly people in the middle, or maybe skewed more towards the right, where we have those few that are way up there. But let's say we took a specific day and they want to know if the average for that day, and they did take a sample of size 36, if that would be more than $32. And we want to find what is the probability of this happening. So we're going to find the probability that X bar is bigger than 32. Okay. The nice thing is, since we took 36 people, 36 is our N, is bigger than that cutoff. So it doesn't matter what the original was shaped because our X bars will be normal. So X bar will take on that normal shape. X bar will have the same average as the original data, which was $20.50. The standard deviation for X bar, the standard error, will be that 3.05, but we're going to divide it by the square root of n. And I'm going to get that value, so 3.0, oops, turn my calculator on. 3.05 divided by the square root of 36, which I know is 6. And I get 0.508, and then we get a bunch of 3s. So it repeats and repeats and repeats. So looking at my picture, we want to go bigger than 32 because it's more than 32. So here's 32 up here. Then we're going to look at this little tail. Again, I'm going to go to SALT to do the work for me. Going back to SALT. Here we will be this time using a right tail because we were looking more than 32. My mean of this problem is $20.50. My standard deviation for the X bar is 0.508 and a bunch of 3s. So I'll put on some bunch of 3s. And I want to go bigger than 32. It tells me very, very unlikely going to happen. Probability of roughly 0. And you're thinking, okay, did I make a mistake? Well, what I would then do is kind of look at my z-score. And we get a z-score of 22.6. Okay, and you could kind of guess, take that $20.50, subtract the 32, or take our 32, subtract the 20.5, divide by our standard deviation, which is 0.5. That's a big number, 22. So that means we are 22 standard deviations away from the mean. That's a lot. If you remember, 68 is when you're within 1, 95 within 2, 99.7 within 3, and I'm 22. 22 is way off the scale. The amount of area above that tail is pretty darn close to 0. So that is not going to happen. This also shows you that I have made up this data because I know a lot of people spend more than $32 at Hy-Vee. And I really doubt that the mean is $20.50. So this is just made up data, but it shows the illustration of what we get. Okay, I'm going to go back to our camera, to our notes. So this happening, my picture obviously was really wrong. 32 is way up here somewhere. And basically the curve is right on top of the x-axis. So that's why we do get that probability of equal to 0. Let's do a couple more. Okay, let's say that the average dress size of all women in the US is claimed to be a size 12 with a standard deviation of 3 sizes. Random sample of 10 women is taken from this population. What is the probability that the average dress size for this group, this sample, is larger than a 13? So I want to know, what is the probability that the sample size, sample average, is bigger than 13? So I need to kind of talk about what X bar looks like. Since we took a sample of 100 women, I don't care what the original data looks like. I mean, I do, but I don't need it because I know X bar is going to be normal or approximately normal. So I can use that normal curve. I also know that where the center of that normal curve is going to be. The center of that normal curve is going to be the same as the average of the original data. The average is claimed to have an average or a mean of 12. So mu of X bar is equal to 12. sigma of X bar, because that's what we're talking about, is going to be the standard deviation of the population divided by the square root of my sample size. And in this case, that's an easy number to calculate for me without a calculator. So that's going to be 3 divided by 10, or 3/10. And my picture, we want to go bigger than 13. Again, my picture is just for reference only. Sometimes my pictures are very off, like they were in the previous problem. But I do this kind of to get an idea that my probability is going to be smaller than 50% because I've shaded less than half of the graph. But I usually go to SALT to get my actual answer. Previous years, we would take and find that z-score and then take that z-score to a table and manipulate the table value. So we're still working with a normal curve. My mean, however, is 12. Our standard deviation, I don't have to worry about rounding this time, is a simple 0.3. And I want to go bigger than 13. And I do get an answer. So we get a probability of 0.00043. All right, hopefully this is getting to be a little bit easier for you as you go and use SALT to find your answers to these questions, and so on. So I did put in the 0.0043. So the probability that our sample of 100 women having a size that is bigger than 13, or an average bigger than 13, is going to be kind of small. And the reason for that is if you grab 100 women, you're grabbing them from all over. You're going to have some down here, in that 100 people, we'll get some around 12. Most of them are going to come from around 12. Granted, we don't know if this is their shape, but even if it was, we'd be still getting people from down here. And we get a bunch of those little skinny ones with the size 2s and the size 1s. But so the probability of this actually happening is going to be a lot harder to do. All right, one last question. All right, we have anthropologists know that the length of a femur bone of a certain animal is approximately normal, with a mean of 36 inches and a standard deviation of 1.5 inches. What is the probability that a sample of 9 femur bones will have an average that is longer than 38.5 inches? Notice we are talking about a sample of 9 femur bones. So we're looking at what is the probability that that sample will have an average that is longer than, so longer, 38.5. We only took 9. So that's not bigger than that magic number of 30. So we do have to look a little harder and make sure that our original data was normal, and it is. So that means we still can do this problem. And I'll write that on here. X bar is normal because X was normal. I also know, so it's going to be kind of like that one picture that I showed you earlier, where this is the original curve and the next one for X bar is going to be a little steeper. I always write them the same. So my pictures don't reflect that. We have a mean of 36. And we have a standard deviation is going to be that standard deviation of 1.5 divided by that square root of n being 9. So we're going to be taking 1.5 divided by 3. So we get 0.5. And we want to go bigger than 38.5. Okay, so we're going to be looking up here. Okay. Part B, I might as well do that as well. What is the probability that this sample, so again, talking about the X bar, is between, so I'm going to put the between 34.75 and 36.5. We're going to be getting that. And again, if we were doing the tables, we would find our z-scores for both of these values, and we'd be looking for the area between those two z-scores. Here we'd be looking for the area between the z-score that this number represents. But I like to use SALT since we have it. So I'm going to go to, draw a quick picture here. So 36 is here, 34.75 is down here, 36.5 is probably closer to 36, but I need to get the numbers in there, so it's a little bit not accurate, but again, my pictures are for reference only. And we're going to go back to SALT to get our values. Okay. So my mean for these problems was that 36, the center, the average of our femur bone. Our standard deviation for X bar is 0.5. And in the first problem, we did want to use a right tail, and we are going bigger than 38.5. 38.5. Which is, again, 0. And if you think about 0.5, you know, kind of doing those magic numbers, an easy thing to see, we can see them down here on the scale too. 1 standard deviation would have been 36.5. 2 standard deviations would have been 37. 3 standard deviations is 37.5. 38.5 is actually 5 standard deviations above. And notice we also get 0 here. So knowing that the previous question we had earlier had 22 standard deviations larger, definitely 0. I kind of wonder how many zeros we had to have before we get a digit, but that is okay. The second question we had pertaining to these same values is a between question. And we are going between 34.75 and 36.5. So 34.75 and 36.5. So I kind of look at my pictures, 1 standard deviation up and a couple standard deviations down, so negative 2.5 and 1. And we do get a value here of 0.83514. Okay, go back to our notes. Let it update a little bit. So again, here we were actually 5 standard deviations above. That's quite a ways away. We did get a probability of 0. It does happen. Here we have a probability of 0.83514. So roughly all the bones that we would find, if we had 1,000 of them, 83.514% of them should fall in that range. I have one more question here. What is the probability that a single femur bone will be longer than 38.5? Now this goes back to a single. So we're not looking at that sample of 9 anymore. We're just looking at a single bone. Sometimes you got to remember that this is the case. We're looking at just plain old X. And going back to the original information, X was normal with a mean equal to 9 and a standard deviation of 1.5. Whoops, 36. So mean of 36, standard deviation of 1.5. So we're going to have to change a few things. So here's our 36 again. Here's my 38.5. Notice that before when we did it of a sample, we were like, what is the probability that a sample of 9 of them will be bigger than this? But here, our standard deviation is going to be bigger. So just be where we might not get 0 again. So let's go back to SALT and just see what the probability would be. So this is kind of looking at the stuff that we had done previously, where we don't have to worry about dividing that standard deviation by anything. So I'm going to change it back to 1.5. We are going to go back to a right tail because we're looking above. And we're going to do 38.5. And here I do get an answer of 0.04779. So we'll go back to our notes one last time. And I wrote it all kind of down. So the probability that a single bone being that far is 0.04 something. Notice though, however, if you would have checked the z-score for that, going 1.5, that takes me to 37.5. Doing another 1.5 is going to take me all the way up to 39. So he was between 1 and 2 standard deviations away from the normal. Makes a little bit different when you look at samples, but you have to remember when you take a sample from a distribution, you're going to get some from all over that distribution, larger ones, bigger ones, and those are going to be pulling the averages one way or another. So it's going to also, that's why the standard deviation shrinks so much. Hopefully this helps. Our next video, we're going to be kind of looking at what happens or what do we do when we don't even have mu? How are we going to start looking at those situations? And those will be in the next video. So I hope to see you there and have a great day.